Hey guys, um, I wouldn't really call this like a tutorial, more like a journal into like just some TA R&D stuff that I've been kind of messing around with over, since I graduated school. Today I'm just going to talk about like some of the stuff I've been looking into for Grid2D. There's a couple really good videos out there already about just how to get started and just kind of how this interface works. Like I said, this isn't really a tutorial. It's more like me documenting just stuff I've been messing around with, and also documenting my learning of HLSL and trying to get better as a TA. So we're just gonna try to create bare bones vanilla Conway's Game of Life. It's actually pretty straightforward, and because of the Grid2D interface, it kind of gets it kind of does a lot of the annoying compute shader overhead that we would have to do if we write it in like maybe another language or another engine. But let's do it together, and we'll do it from scratch. So I guess first of all, here are the rules for vanilla Conway Game of Life. So there's 4 main rules that we'll have to iterate through our basic grid stack. So let's begin. We're gonna make a empty Game of Life demo. We're gonna make a Niagara system, and we're also gonna need a where is it? Gonna need a render target. RT demo. And the cool thing about render targets, cool thing about Grid2D is that we really don't have to. We can set all the settings for our render target inside our stack, so we can just like make it and forget about it. So let's get in here, and we're gonna make a empty emitter. Let's name it Game of Life. And we're gonna make our sim target GPU fixed, and we're not gonna need particle spawn or particle update at all. We don't even need a sprite. We don't even need sprite render, to be honest, because we're not really rendering any sprites, that is. And let's see how we should approach it. Here, let's make some. Let's set some parameters directly first. We're gonna make 2 ints, and these ints are gonna be so x and so y. And what these are going to be is basically the dimensions of our grid. In this case, we'll start small, maybe 256 by 256. We're also going to need our grid. So we're gonna let's be organized here, and then we'll do another one after that. Because I think let's rename this into set grid dimensions, and then we're gonna set data interfaces here. And in this, we're going to create our grid, and we're going to create a render target. The grid we can leave as is, because we're going to set it right after we do this. But for the render target, in order to have access to our guy right here, we're going to need to pass in the data from outside of the Niagara, this system stack. And the way to do that, not just with render targets, but with like any other sort of data, is just through user parameters. So we're gonna get render target, and you'll see that there's 2 of them here. The difference is that this texture render target is the object that we're pointing to, and this render target 2D is the data interface that reads from this texture render target. So in this case, we need a texture render target. We'll call it RT. And we're going to set this as our RT. And under here, we'll set that there. And sorry, this isn't really like a Grid2D beginner overview. Even though I feel like if you just follow this, you'll kind of get the hang of it anyway, right? And like I said, there's plenty of better videos out there that kind of, actually I am good at teaching you how to explaining stuff, I guess. So we have these two things. We have set up our dimensions, and we instanced the two interfaces that we need. Now, we'll make a scratch pad called init interfaces. And basically here, we can grab our grid, and our render target, and then we will set our cells. And we do it in the scratch pad, so we don't have to go and reset it every time outside of it if we ever change stuff, And we're not setting anything directly, so we don't need that. So, yep, like that. And then we're just gonna drag these here, and then these are also gonna go here. So that way our grid and our render target both share the same resolution. And the resolution, if we go out here, gotta hit apply first. If we go out here, we can see the resolution. We're gonna use the one we set up here. So we can just write cells X, cell Y, and then the grid, we'll use the grid we made earlier as well. Render target, cool. So that's all the setup for, that's all the setup we need. And next is, I think a lot of, and to be, first of all, to get one of the people that I think do a really good job at teaching Grid2D is Overdraw XYZ. I learned a lot about how Grid2D works from him, and a lot of other people like Andreas and Asher all have really good videos about how this works. And I got and I learned how to basically set up our data interfaces properly from watching their videos. So I think when a work comes with data like Grid2D and even Niagara stuff, it's always good to split up our steps into, it's always great to kind of truncate our steps into stages. So let's think through what we want to do, right, with these rules. So first is we'll have to initialize a blank grid. So this is our grid of 256 by 256 elements. And I guess how compute shaders and how Grid2D works is that when let's say we just make a stage, right? And this is called init grid. And what we do here is we can choose a iteration source. We'll choose data interface, and we'll bind it to our grid. And what this does here is when we bind this data interface to this simulation stage, is that it'll look at this data interface here, and it'll see what the resolution is and whatever. In this case, it's 256, so it's got 256, cells on X and on Y, et cetera, et cetera. I think what's happening here is that it will automatically read this interface and execute a thread on the GPU for each one of our grids. So each of these grids will calculate asynchronously, and that's why compute shaders and Niagara particles and stuff are fast and really cool. So anyway, hope that kind of makes sense, and hope I'm right. If I'm not, then at least it still works. So in this init grid thing, we'll make a scratch pad, and I think it's always good in this init grid to always have a stage that you're initializing all your attributes in, right? So in this case, we don't necessarily need a map get, you might think, like I did when I first started playing with Grid2D, that for every stage you need to kind of like reference this Grid2D and do some and like, oh, I gotta set I gotta set values or whatever. But you don't really, because like I said earlier, we're already binding this Grid2D interface to this stage. So when we do this, it is already generating the threads and running GPU calculation stuff on every single cell, right? So it's already doing that. So we don't need to, like, if we're only setting a value, we don't really need to like specifically say, go in and write this again. And oops, sorry, here we always have to stay organized. Init attributes. And when we think about it, for this example of this game of life sim, we really only need one attribute, which is this living in a live state you have to keep track of, right? So we'll make a float, call it alive, and by default we'll set it to 0, and then we'll set that to stat context. And basically stat context is how we're gonna flow our data through the entirety of all our sim stages. And basically that's it. So, and to prove what I said earlier was true, and that we don't need to like specifically call on our grid interface in the actual scratchpad, apply this. If we go up here into when we instantiate this stuff, there's a preview attributes tab, and we click on our Grid2D, we can see all the attributes that currently exist within this Grid2D interface. And currently you can't really like specify which variable we want to see, but I think hopefully Epic makes that a thing later on. But for now we only have one variable living on our stack of grids, and that's alive. And if I set this to 1, you'll see in our preview thing it turns to 1. Cool. That's a good way to see if things are working too. So we've got that. So, and now we need to make another stage, and we'll call this stage randomize population. And basically what we want to do here is that we're just going to randomly go through, for every cell on our grid, we're going to want to basically randomly say if it's alive or dead. And this is an easy way to get set up and just run our simulations with. Obviously there's other ways to have a starting state for a game of life. Like you can use a texture, you can like have you can draw stuff on it using like your mouse, and there's other very cool and specific starting states you can set up. But just as a quick proof of concept, I guess, we're just gonna randomize everything. So same thing, in this stage, set our data interface to the grid. And I forgot earlier, in this initialized grid and for this randomized population, we only want to run these on reset. So these aren't going to be calculated every frame. Otherwise, it's not going to look very nice. So in here, another scratchpad, randomize population. And for now, we're gonna, let's see, I don't think we need the grid thing. I don't think we need our grid here either, because all we really need to do is, let's get a float. This float will be max chance, I guess. We'll call it chance. And basically what we want to do is that we'll, actually maybe not a float. Let's just do an int. And then this will be spawn chance. And we're going to use this as the random int, as the random integer. And if we see what this random integer function does, it returns a random integer value between 0 and max minus 1. So basically, we're just going to say, for every cell on our grid, we're going to be like, hey, between this and this number, if this number equals let me just do this. Subtract int 1 branch. So it's saying, let's say, for example, our spawn chance is 2, right? So when we're trying to aim for 50%, so 2 max integer returns between 0 and 1, and if our thing is 1, that means we're gonna want that grid. We want the cell to be alive, right? So 50% chance of each cell to be alive. And here, if it's true, we'll return float. All right, it's not float, we'll return 1. And if it's not true, it'll stay, it's already there, it'll stay dead. And then what do we want to set this value as? We want to set it as this one. So we can just make a float alive, and then we'll set that to the stat context. And because this is the same name and using the same, because this value is using the same namespace and it's named the same, it's the same value. So if we plug this in, apply, and then we'll set this to 2. You can see down here in our preview that it's working. So it had a 50%, each grid cell had a 50% chance of either being dead or alive. And right now, red means alive. And it doesn't really mean, because I think the thing is that each grid channel is like an RGBA value. So it's kind of like the UVs in material graphs. It defaults all its rendering as a vector value. So even though our alive thing is a float, it's still treating it as a vector here. Okay, so we have set up our initial attribute, and in here we have set up our starting state. So next stage, we're gonna game of life. We're gonna run the algorithm on it. So same thing, we're gonna use the interface, which one we want. We want the grid. And this one we're going to want to execute always, right? So let's call it game of life. And this one here, we finally want to call on our grid, because we're going to need to know specific stuff about specific indexes and specific stuff about our neighbors, because that's how this game of life sim thing works, right? Because let me just erase all this. Because what we want to do is for every grid cell, we're going to say this is our current grid cell. We're going to want to look in every single one of its neighbors. So it's going to look, this is you. You're going to look in for 8 directions around you. And then we're going to have to add all these up to see what happens, basically. And in order for us to have access to all our neighbors, we have to use our grid interface. And for this one, if we use nodes, it's going to be very messy, because we're going to have to basically sample something 8 times. So we're going to use a little bit of custom HOSL, which I just recently started learning too. So this is also a good chance for me to, review and make sure I'm not fucking anything up. And for custom HOSL, I think it's also pretty straightforward. We're going to need to take in our grid value, and then we already know what we want to output and set. So we're just going to make it a float called alive. Actually, I think we might not be able to call it alive because there's already a, oh, it likes my misspelling. So you know what, whatever. And we know that we want to set this to our other alive float. So we're gonna leave that there and connect it later. It's always good to just compile your code, I think, here. So we're not like, you know, I don't think there's that much of a difference, but whatever. And another thing that we can do is if you right click on any data interface that you plug into this custom HLSL node, you can kind of see what functions are available to it. And the functions we want for this one is get previous float value. And if you click on it, it copies it to your clipboard. So if you paste it, it kind of shows you what everything you need basically. So grid, this is the grid. Get previous float value, that's the function name. Attribute is, well, you know, the attribute that you want. You plug it in here. In is basically the inputs of the function, and it tells you what thing it's expecting, what data type it's expecting, and then out is kind of like the return value that's going to be you know, popped out of this function. So we want the alive attribute, and actually I don't want this one yet. We're going to come back to you, but as you see, in order to use this function, we're going to need something called index x and index y, and we can get that from our grid as well through execution index to grid index. Copy that, paste it, and you can see that this grid takes this function and it actually only returns the x and y of each index. And what this basically means is that if we look back to our grid, the execution index, much like if you've done other stuff with Niagara, each particle, when you do particle stuff with Niagara, right, you have a execution index list, and it's basically like an array of each particle coming out one by one, and it kind of shows you like which particle was emitted first, and then second and third, etc. Same thing here, more or less, but instead of particles, it's cells on our grid. So execution index to grid index basically takes a 1D representation of our grid cell and gives us a x and y version of it. So here we see that it wants a int x and an int y, and we can make that up here, int x, y. And we're going to take out these and replace it with our own values. Cool, and that's kind of all we need there. And then what else do we need then? So now that we have that, we can get back to this part, which is we're going to need to sample like we did here. I erased it, fuck. What we're going to need to do, basically, like I said earlier, we're going to have to do this 8 times, right? So 1, 2, 3, 4, 5, 6, 7, 8. Cool. And then we're also going to need, since there's 8 out values, we're going to need to make 8 of those. So it's going to be float, and the 8 values we're going to need is obviously the directions that we're going to sample from. So left, right, up, down, up, left, up, right, down, left, down, right. Cool. And actually I lied, we need one more, because based on this thing, we also need our current, we need to know the state of the cell we're currently at. So we're also going to add cur. And actually, so we need to sample this 9 times. And we're going to do that first and separately, so we don't confuse ourselves. And for here, we can take index x, and then here, index y, and then the out value, we're going to save it in cur. And so basically, we're going to do this for every single one. So I'm just going to quickly run through all of it. I'm going to quickly set it up, and then we'll try to like map out where everything is basically. So x, oops, x, I'm probably gonna cut this out. All right, cool. So now we just kind of have to think of every direction in terms of like UV coordinates. So first one is left. So if we are, going back to this, if we are sampling to the left of this, and then this is our x. Oh, that's actually a bad place for it. X. Whoa. X and y. In order to sample the left of it, would be we have to -1, right? So -1, and then y would stay the same. And now we're gonna save this in our left value. Okay, and then next for right, it's going to be the opposite of that. So +1, right. And then for up, y +1, up, down, obviously that, down. And then now for up left, we want this guy, it'll be -x and -y. So x -1, y -1. This will be up left. That means for up right, it'd be +1, -1. Up right. And then next we have down left, which would be -1 in x, but +1 in y. And then lastly, +1 for down right. Cool. So we now have, if we wrote this correctly, we now have all of these variables ready. And that means we are ready to put all these rules in play. So let's do the first one first, right? Under population, any currently live cells with fewer than 2 neighbors will die. So I think we can so let's do this part first. So it will be if cur equals 1.0, which means alive, right? And I'm gonna format it like this. If that happens, and it has fewer than 2 neighbors, so we're gonna have another if in there. And if, before we have this, getting ahead of myself, we're gonna have let's just do count. I'm lazy. We're gonna have to sum all these up. So left plus right plus up plus down plus up left plus up right plus down left plus down right. There we go. So if we do it this way, and since we only have 2 states, 1 being alive and 0 being dead, right? This is all going to add up. And we can see how much we can like use that as like a metric for how many neighbors around us are alive. Anyway, back to this for loop. So if currently we are alive, and if, let's see, what is it again? And if count is less than 2, then alive equals 0. It means we died. Actually, I'll format it a bit better. So My eyes don't bleed. Else we continue to live. So that's our first if. And then that's our first row here, under population. Next one is any live cell with 2 or more live neighbors will keep on living. And then any currently live cells with more than 3 live neighbors will die. Oh, we have another requirement that says any currently live cell, which we already are in this loop for, with more than 3 live neighbors die. So that means it'll be either this, or if count is greater than 3.0, we be dead. So in both cases we die. So we have this one, we have older population and underpopulation figured out basically. So we have survival, any live cell with 2 or 3 live neighbors will keep living, and any currently dead cells with exactly 3 neighbors becomes alive. So we'll need a else. Just do, honestly we can do an, whatever, we'll just do else. And then we'll do an if inside. If our count equals 3. Any currently dead cells with exactly 3 live neighbors becomes alive. So 2.0. Right. I think that's it. What else are we missing? Let's read through it. Any currently live cell with fewer than 2 neighbors will die. That's this one. Alive, less than 2, dead. Any live cell with 2 or 3 live neighbors will keep living. Any live cell, so alive, with 2 or 3 neighbors, else, which I mean, it's kind of like this, I think that's encapsulated in that statement. Any currently live cells with more than 3 neighbor dies. If you have more than 3, you're dead. And then any dead cell with exactly 3 live neighbors becomes alive, which means if it's not true, then we're in the else. And if we have exactly 3, then we're alive. Yep, I think that's all of it. I mean, if it doesn't work, it doesn't work, right? So now we plug this in here, and then we press apply. Oh, well, something happened there. That ain't right. Let's see what we did wrong. Else, we need to set y equals 0, 0. There we go. Cool. We also need this statement. And also, another thing I forgot is that every time you finish a scratch pad, especially in Grid2D, always make sure to, link it up outside. So now, in our little preview here, you can see that we have our game of life logic working. Yay. But this is still only living within the stack context now. We'll need to write this grid onto our render target that we have set up earlier. And to do that, we'll need to do one last stage. Right to RT. This, and same thing here. And then scratch pad. Right to RT. And basically, have to do this all. And this one's gonna be very straightforward. We just need a grid. And then we'll need our render target. And then the render target, since it's the same exact resolution, we're not gonna have to resample it or anything. So under RT, we can just do set render target value. The value we want to set is get previous float is alive. And then we're gonna need to make this a linear color. And then we're also going to need these indexes, which is basically what we did in the last one too. So exact grid index. Now we can plug this here, 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 and here. And once again, we're not setting anything, so we don't need it. Now we'll plug this here and output it. And then once again, we're going to need to go outside and link up our data interfaces. And then if that worked, we can click into our render target. And then every time we compile and play, you can see it working. Turn these off. Nice. So as you can see, it really wasn't, and you know, I mean, getting it set up is kind of annoying, and understanding kind of how it works and how to pass data through simulation stages can be kind of like a drag. But you know, once we work through an example, it's really not too bad. You know, you're just kind of like passing data from one place to the other, and then once you have like, you know, simulations going, this is really powerful because we can choose very specifically what to do with each one of our data, right? And then you can like choose different things. You can add different rules in here. It's cool, and I'm still, you know, learning about it and stuff and having fun with it. But I think for now, and you know, like once again, sorry if it's not really well explained. Not really a tutorial again, but that's it for now. At the end of this journal entry, and maybe I'll make another one in like 6 more months.